please come up stage and give us your presentation. Thank you very much, Dr. Steiner.
Thank you very much for the nice introduction, and I promise to keep it short a little bit. So this talk is not about to convince you that deterministic Ethernet is the most advanced network on the planet and actually in the universe, as you have seen. But it's more intended to give you a kind of a background on why deterministic Ethernet looks as it looks today. Let me start with a short introduction what we mean by oriented basic research, and I took this well-defined definition. Oriented basic research is research carried out with the expectation that it will produce a broad base of knowledge, likely to form the background to the solution of recognized problems and future possibilities. So it's the notion that you generate a broad base of knowledge that would lead to specific solutions to problems that we have right now that are likely to occur in the near future. So it's a very personal view on where you set the beginning or the origin of a technology such as TTT Ethernet or deterministic Ethernet. And it's my personal view, and I think it's probably shared by a lot of people, that the origins of this technology, of the deterministic communication, is in the development and the research of time-record communication, like the TTP, the time-record protocol, that dates back to 1994 in the 90s. And then a more system-based view that takes the time-record protocol as one of the building blocks to generate or to design guidelines and blueprints on how to design deterministic systems. And very happy that this is one of the core papers that the technology of our company is based on and was recognized by receiving the Jean-Claude Award, I think 2 years ago, in Dependable Systems. So let me talk a little bit about the time-record paradigm. And we've heard this before, and I'll cut it short, really. But it boils down that you have nodes, and a node may be in operating systems, it may be processes or tasks. When we talk about a network, we talk about end nodes or switches. So you have nodes, and they have local storage of time, a local notion of time, which is in software a variable probably, in hardware it will be a register. So the idea of synchronizing is nothing more than guaranteeing that at any point in real time, those distributed variables, those distributed registers, have approximately the same value. And by approximately, it's important to realize that the maximum error, the maximum difference between the values in the different registers is bounded and well known as system design time. So once you have that, all you have to do is to schedule events like the transmissions of frames offline as we do it today. You derive a schedule that tells you at which points in time, in respect to this global time, things have to happen. And an example is given here in time-record communication. I've visualized in a short animation here. We have the communication schedule on the bottom here, this envelopes, green, red, and blue. And then you have the network, where we assume that all the end nodes, the network interface cards and the switches have synchronized clocks, have knowledge about the schedule, and all you have to do is you execute the schedule. So what that gives you is a deterministic notion or a deterministic knowledge on what's going to happen in the network when you transmit messages, when you communicate information. It gives the nice advantage for real-time communication that if you had a packet like the green one with the X, that you need to transfer through the network very fast and with low jitter, this notion of deterministic communication by time-record communication ensures and gives you this guarantee of real-time transmission. So coming back to this notion of oriented basic research, and here is a selection of topics that actually came out of this basic research on time-record communication. I'll start with photon clock synchronization, so algorithms and methods that guarantee that those local timers are synchronized to each other. And I reference here a paper that actually dates back in the 80s, and I shouldn't mention that, of course, Professor Poppets and his team was not the only one working on these topics, but there have been famous people like Leslie Lamport or Basil Smith or Nancy Lynch working on this topic. So in the 80s, this was that big thing. How can you how can you design protocols that would guarantee you, even in the presence of failures, that those local variables stay synchronized to each other, have approximately the same value. Fault clock synchronization is one thing. The other thing is the communication schedule. So how do you derive this sequence of envelopes? How do you derive this structure? How do you find points in time when you should do things? In our case, this means still we are doing this offline. We're moving currently to an online dynamic scheduling approach. But it's not only finding the solution, but it's also how do you then execute the schedule in a device. So there are quite smart algorithms that you can apply to make this efficient in a device. Then there are some more topics like membership services, which are kind of low-level diagnostic mechanisms that realize that locally, if your local clock deviates too much from other clocks in the system, or local central guardian schemes that allow to tolerate certain malign failure behaviors. For example, if you had a switch that starts babbling messages, how do you tolerate that? If you have an endpoint that starts sending any form of messages, any garbage to the network, how do you stop the node from influencing the complete network? So all of these topics go into this research of local and central guardians. And then of course, as we have seen, using the concept of a deterministic time-regard protocol as a building block of a huge of a deterministic architecture. So this background of knowledge really translates into solutions that we have today. I just depicted some pictures of TTP nodes, the time-regard protocol, and on the right side I give you some examples where these products are used today. Namely in large aircraft, we are very proud that the TTP solutions are used as well in Airbus A380 as well as in the Boeing 787. And then of course there is FlexRay, which is another solution based on the background of knowledge that was researched, which is quite successful in the automotive industry. So the world spins around, and while we are developing these cool time-regard protocols and time-regard architectures, we see that embedded systems nowadays are problem everywhere, and it's growing beyond comprehension sometimes. So what we have seen, what we have observed, is that integrated architecture suddenly became feasible. So the idea that you have big or moderate size computing nodes that would be able to host applications that have mixed criticality properties. And by mixed criticality, that relates to both, or to various aspects, to mixed criticality in the time domain, in the safety domain, as well as in the security domain. So the idea was, well, if this is happening right now on the node level, the capability of hosting applications with mixed criticality, this can and should extend to the network. So the network should be able to again, also host applications with mixed criticality. And this, of course, means, or the motivation behind that is that you don't want to have private networks that connect the integrated nodes together. So you want to have one unified network that connects nodes there, where the nodes themselves are able to host applications with criticality. Let me give you a small example here. This is an automotive network that I just built up. This consists of ECUs, electronic control units, and the ECUs are connected to each other with a network, and for simplicity we just assume it's an Ethernet network. So what we really want to achieve is the notion of mixed criticality on the node level, where you have hardware and software measures in place that guarantee you inference freedom or minimize the interference of the tasks from the different applications on each other. We want to extend this to the network. And by doing so, we want to guarantee that this network is capable to host applications that have real-time capabilities or real-time requirements, as well as applications that don't have these requirements for real-time communication. And then again, research has been conducted, and one of the networks that solves this problem and meets these requirements is the time-regard Ethernet. And here a reference paper from 2005, where it actually says in the first sentence, this paper presents the rationale for an outline of the design of a time-triggered Ethernet that unifies real-time and non-real-time traffic into a single coherent communication architecture. So it's key that we want to use one single physical network to host the applications in your system, all the applications in your system. We want to minimize the number of different buses that you use in your system. Some specifics to this early prototype, just to give you an idea, is that this was fully compatible to the IEEE standards. So when we talk about Ethernet, we typically refer to two things, to IEEE 802.3, which defines the physical layer and the MAC layers, and we talk about the IEEE 802.1, which defines functionality that's implemented in network switches, for example in Ethernet switches. And this solution, this first prototype, actually supported this mixed criticality requirement that we had by providing time-triggered communication, as well as providing standard best effort communication. As a design detail here on this prototype, these switches were designed to be as small as possible. They have a very simple design for cost reasons, of course, but also for the reason to argument that this small, less complex, little complexity device does not behave malicious in the failure case. So as a consequence of this design to have the switch as small as possible, a preemption mechanism was implemented. Preemption means that if the switch was in the process of transmitting best effort frames and it receives a time-triggered, a high criticality frame, it would preempt the best effort frame and forward the time-triggered frame to achieve shortest latencies possible for the time-triggered frames as well as shortest transmission jitter. I use this as a design detail, as you will see in the following, how this translates then into products and the technology portfolio that I'm going to talk about. And Ethernet, as probably all of you know, is a success story on its own, so it was quite reasonable to move towards an Ethernet-based solution when talking about the mixed criticality system. In fact, Ethernet has celebrated 40 years in 2013. You're probably familiar with various industrial Ethernet variants that are out there, like Profinet, EtherCAT, Ethernet PowerLink. And for us, quite relevant, the avionics version of Ethernet standardized by the ARINC standardization body as ARINC 664 Part 4, also known as avionics switched for duplex Ethernet. So we had this basic research in time communication, mixed criticality communication, and translated that into a prototype. So the question becomes, how shall the product look like that comes out of this technology? Well, from day one, we wanted to have the time-triggered clock technology to be cross-industry, and you've heard it a couple of times here in the previous talks. So the idea is that you generate the technology and generate products that you can use in various markets out there. But it just happened that at the time when we moved to productization of the technology, the avionics market was the one that was most interesting to us. So we had to shape the TT Ethernet prototypes, the TT Ethernet product into something that would fit the avionics market very well. So we used the avionics Ethernet that I just mentioned before as a baseline technology and designed the TT Ethernet functionality as add-on services kind of to this IFTX basic protocol. At the beginning of this conference, here are some pictures that show Orion again. So here's the capsules, and here is the Orion crew module tied together with the ESA service module, and a launcher that has to be still be finalized, and here launcher board system. And here's the real thing. So this is the Orion crew module that uses a time-triggered bus. Here is a short overview about of the network. So here again you have the command module, the Orion crew module. You have an adapter in between the crew module and the ESA service module. And you see the red thing is a time-triggered gigabit Ethernet. And one reason for NASA to move towards this technology was the capability to integrate best effort and time-triggered communication, as well as reconstraint traffic on the same network. So instead of having physically separate networks, you're suddenly able to integrate everything into a single physical network. So, you know, the NASA project Orion is a cool project, and it's very interesting from a scientific perspective to work on. It's actually a very profitable product for TTTech also. But the point is, we want to come back to our original goal to broaden the application market for the technology, for the products. So we don't want to be only a special provider of space hardware for for this kind of programs, but we want to target all these markets that are out there, and I have some depicted on this slide. So we want to go into avionics, we want to go into renewable energy, we want to go automotive, railway, industrial, and process control. And really, we have already running products out there in space, avionics, and renewable energy. There are various evaluations right now in the automotive and the industrial domain. They'll come late, in 2 or 3 slides, I'll come to that. That's mostly driven by the developments around Ethernet. So there is a big industrial trend in the automotive and the industrial world to use Ethernet as the one and only communication protocol for their purposes. And by the way, on the right there are some form factors that we use in our project. So how do we do that? We just can simply take the silicon that we develop for space and offer it to other customers, other markets. So we have to establish some sort of a product variant. Yeah? And there are different dimensions and where you can scale or vary the product. So it's, of course, from a switch perspective, the number of ports the switch provides, speeds, shall it be 10 megabit, 100 megabit, a gigabit. Now we're working on 10 gigabit deterministic Ethernet solutions. Different form factors, you've seen it on the previous slide. Different safety standards, we have mentioned safety before. Then whether you have a device that's only able to switch network, switch traffic in network, but shall this device be intelligent? So do you want to integrate end systems and hosts? So how much do you want to integrate? And then different functionality, and then it comes back to standards. So really what we see is, right now you are right in the middle of a technology revolution. We have heard the topic of Internet of Things already, but really from a technology perspective, we see this as an IT-OT convergence. So we see it as a convergence of information technology and operations technology. So operations technology would be what we typically worked in embedded systems, control of robots, of cars, of planes, these kinds of application areas where we traditionally came from. And information technology is what we all use in the office technology, what we're used to communicate, what Google uses. This is where the big Cisco, Marvell, Broadcom come in as their standard IT network providers. And I think that this integration of IT and OT technology is actually one of the big motors behind all these smart start developments. Because this integration of existing embedded technology together with IT technology makes a lot of smart developments actually only possible. So for us, OT networking people, and I'm speaking about me and probably my colleagues in TT, so we are concerned with how to make sure that the network works in critical applications. It means that, like Ethernet, there are more IT standards entering the OT domain. And by standards, we again come back to what we said earlier. So we did standardize the TT Ethernet technology as an SAE standard, but really the market, especially automotive and industrial control, sees the home of Ethernet being the IEEE. In particular, the standards I mentioned, the IEEE 802.1 and IEEE 802, 802.3. So what happened there is that parallel to the development of TT Ethernet and deterministic Ethernet, these standard bodies moved into the area of real-time communication with a technology called AVB, with audio-video bridging. And right now, people are moving, or this group is moving into hard real-time and fault-tolerant communication. And one example of projects that are currently worked, and actually right now being finalized, is the 802.1 QBV standard that standardizes a time-record paradigm inside the core Ethernet standard. So when you buy a switch chip, in 1 or 2 years from now, from one of the big vendors, this will have this time record capability built in. And then, of course, preemption. So we just designed it out, now it's begging. So here's just an overview how this works. I'm not going into that because of time reasons. This is an overview of QBV. We can talk about that in the break if you're interested. But the important point is that we as a company engage in this IEEE standardization activities. And we are doing that since very many years. It's January 2012, so it's more than 3 years now. And we are committed that we extend and add on from a functionality point of view, extend the functionality towards these standards that are being finalized right now, and that will be finalized in the future. But then we are not doing that blindly, but we focus on what the market needs. So as we've heard, we are just 500 people, we cannot do everything. You know, the Cisco, we need to be very careful to have our ears at the customer at the market and realize what's really needed out there, so we don't build these huge monsters of switches that you can find from other vendors. So that's the status quo. Regarding the future and probably current business already, we already have had this slide from Andreas that shows that there are a lot of challenges and opportunities actually on the road. There is this huge chance of autonomous and piloted driving, where you think that the deterministic communication platform on its own is able to contribute to this technology or to this movement, as well as the architecture designs on a node level that Andreas presented. Then safety was always our core expertise, and then the real-time of things, meaning this IT-OT integration that I was talking about some slides before. We target strategic research in various areas like wireless communication, configuration management, which is actually one of the key topics in IT-OT integration. So there we're looking into software-defined networks, these kind of aspects. OpenFlow is a key topic. How can we integrate these technologies that's available in the IT environment since years into the OT environment? Security, and then how do we apply that, for example, in an application, for example, deterministic computer vision. So here, a quick summary, and I have one more slide. Just shows you how research, basic-oriented research, contributes to products that we actually successfully deploy. And we have these research blocks that I sketched here as a step. So this research, different steps rely to some part on each other. We are able to build solutions based on this thorough scientific foundation, like TTP, TT Ethernet, and now upcoming Ethernet products that integrate also these IT-OT concepts. And this is not a one-way road. So it's not that we research something and then we generate products out of that. It's important to realize that from the products we get a lot of feedback back on how to steer and where to look at in our research. So with that, I would like to conclude. Hope I made the time budget. Research in time communication and time-regal architectures has produced a broad base of knowledge, and I hope I've given you some hints on products, projects, and products that are out there that use this research outcome. Solutions have been built successfully and deployed, and coming back to this stepwise increase of research, it's important to have this continuity in research, also to keep on continuously producing interesting products for the market, for various markets. That I'd like to thank you very much for your attention. I have some links of interesting activities coming up, for example, the Deterministic Ethernet Forum, which will be hosted here in Vienna end of October, and the agenda is online. It will be talking in the area of this IT-OT integration, what it means for a network. So thank you very much. And if there are any questions,